In section 6.4, we're going to go over yet another application of trigonometry. This one is going to create for us a new system for graphing called a polar coordinate system. So this polar coordinate system, what is it? A polar coordinate system is a plane with a point O A polar coordinate system is a plane with a point O called the pole and a ray from O called the polar axis. Each point in a plane, we have a point in the plane, each point in a plane is assigned a directed distance r from the pole and a directed angle from the polar axis. Graphing in polar coordinates is somewhat similar to graphing in rectangular coordinates, as we've done most of our lives, in that we need two pieces of information. In a rectangular coordinate system, you need an x and a y. You need to know how much measured from the origin do you go left and right, how much do you go up and down. Well, so similar, we need two pieces of information. We need to know, in this first example, the 6 tells us how far do we go from the polar axis, not the polar axis, from the pole. The pi over 3 tells us at what angle do we go from the polar axis. Okay, so two pieces of information here. And so what you see here is a polar coordinate grid. So it's not rectangular, okay, it's not squares, but it's made up of concentric circles, kind of concentric rings. And these particular graphs, the ones that I found to put in the notes, they have one extra line that we're not going to use. For instance, this is 0. Here at the top is pi over 2. The one in the middle is our pi over 4. And then right here is the 30 degrees. This is pi over 6. This is the 60 degrees. This is pi over 3. And then these lines we're not going to use. Those extra lines there, this particular polar coordinate grid shows lines coming out of the pole every 15 degrees. And so our unit circle, the one we built, was on 30, 45, and 60 degrees. And then of course we skipped to 90, so we just we'll skip this extra line. It's right in there. Okay, so if I want to plot the point 6 comma pi over 3, it's done by going up to the pi over 3 line. Okay, so I'm going to be on this line right here, and I'm going to count 6 units out from the pole. So just 6 rings out from the pole. So 1, 2, 3, 4, 5, 6. And there's where the point plots. Okay, the next point, -4 comma 3 pi over 4. So first of all, let's just kind of figure out where is 3 pi over 4. Okay, 3 pi over 4 is in the middle of quadrant 2. There's 3 pi over 4. Okay. Now this one's a little different than the last problem in that we've got a negative r value. Okay, our distance from the pole is negative. Well, when we go on the 3 pi over 4 line, so if I go out here towards 3 pi over 4, I'm counting a positive distance from the pole. I want a negative distance from the pole. So on this 3 pi over 4 line, we're going to count in the negative direction, so just directly opposite, 180 degrees opposite. And I'm going to count out 4. So it's going to put me at 1, 2, 3, 4. Okay. As you can see, I'm on the line that puts me, again, just directly 180 degrees opposite of 3 pi over 4. I just went the opposite direction. I went in, so the opposite direction, kind of like the negative direction. Okay, finally, the last point, just to practice plotting, 7 comma -45 degrees. So let's find first where -45 degrees is. It is in the middle, directly in the middle of the 4th quadrant. Here's the line that represents -45 degrees. Now I want to be on that line. I want to be on the -45 degree line. I'm going to count out on that line 7 units 7 units from the pole, from the center. Okay, so on this line, 1, 2, 3, 4, 5, 6, and 7. And there's my point 7 comma negative 45 degrees. Okay, so just a few examples of, again, plotting points with this system. Again, we need two pieces of information. We need to know how far from the pole are we, and at what angle off the polar axis are we measuring. Okay, those two things. We can plot any point in polar coordinates. Now, we're going to find it quite helpful to be able to convert points back and forth between the two systems of coordinate systems that we have. We have the rectangular coordinate system XY that we're real familiar with. We're definitely pros at graphing points in XY, and then we've got the polar coordinate system, which graphs in terms of r and theta. So it'd be nice to be able to take these new kind of unfamiliar points and convert them to rectangular coordinate points that we're very familiar with, and then potentially vice versa. So I'm going to give you a pair of conversion formulas for each, going from polar to rectangular. Okay, so this one's going to take us from polar to rectangular. And then this one's going to go rectangular to polar. Okay, so a couple of conversion formulas for each. So if r and theta are known and we want x and y, the conversion formulas will be this. X equals r cosine theta and y equals r sine theta. If I want to go from rectangular to polar, r squared equals x squared plus y squared, and theta equals tan inverse y over x. Those formulas should hopefully look, in some sense, vaguely familiar to us, because we can almost think of plotting a point on a polar coordinate system as like seeing a vector. And being able to find magnitude, direction, trig form of a vector, etc. And these formulas are really just kind of variations on those, just with different lettering in place. Next, let's do a couple of examples of just point conversion. This first one is wanting to go from polar to rectangular, so that means that this is an r and a theta, and we want to find the x comma y point, okay, that is equivalent to this r and theta. Well, the x point, and x equals r times cosine of theta. So the r, I've got 2.5. I'm going to go ahead and use a fraction, 5/2, times cosine 17 pi over 4. So we got 5/2 times cosine of 17 pi over 4. I want an exact value, please. Let's not go with decimals. So 17 pi over 4 would be the same as pi over 4 on the circle. So that would be square root of 2 over 2. And so we get an x value of 5 square root of 2 over 4. The y value equals r sine theta. So it's going to be r, which is again 5 over 2, sine 17 pi over 4. So y equals 5/2. Sine of 17 pi over 4 is also square root of 2 over 2. So we get 5 square root of 2 over 4. So our xy point that we want, 5 square root of 2 over 4, comma 5 square root of 2 over 4. Okay, another example, this time going from rectangular to polar coordinates. So what we have is an x comma y. What we want, what we need to find is an r comma theta. The r value comes from the equation r squared equals x squared plus y squared. It essentially comes from Pythagorean's theorem. So that's going to be 1 plus 1, or r equals the square root of 2. The theta is tan inverse of the y value over the x value. So that's tan inverse of -1, and if you do that on your calculator, you're going to get a value of negative pi over 4. We have square root of 2, comma, negative pi over 4. Now, we've been becoming real accustomed to checking angles to see if they make sense in the context of problems. Let's see if this negative pi over 4, would this make sense? The rectangular point -1, 1 plots here. Okay, so I need some sort of polar point that plots here. So let's think if this is a polar coordinate system. We've got the concentric circles right here. Is the point here? It's in the positive direction on this line as far as it's moving away, but this angle theta, is it that angle? And the answer would be no, it's not that angle. The angle that the calculator gave me is this angle right here. All right, well, what do we want? We want the other side of this angle. We need to add to that, if this was in degree form, we'd add 180. We need to add to that pi, the point that we actually want, square root of 2, comma, 3 pi over 4.